Hello everybody, welcome to today's COSI seminar. We have Dr. Richard Clelland from GUI. He's the manager of research and development systems at GUI. He holds a BA in mathematics and physics from the University of Pennsylvania and an MA and PhD in mathematics from Duke University. And before working at GUI, he held positions at Stony Brook, New York University, and here at the University of Colorado. He's here today to talk about feature extraction problems in satellite imagery. So, okay. Welcome.
Thank you. So, thank you for having me. It's nice to be back. I'll turn off the nice little slideshow you're not going to see and get to the talk. So, here we go. So, I'm going to talk today largely about how can you get features out of imagery, or what we're trying to do that. And by features, I mean anything of interest, really. And you can think about buildings, or roads, or rivers, or double-line drainage, whatever you want. Okay? So let's see, is that going to work? Real quick, I work for a company called GUI. We are one of 2 commercial satellite companies in the US. We currently have 2 satellites. We have Iconos, which we launched in 1999, which images at 0.82 meters resolution at nadir. Okay? We have GUI-1, which is half that, so it's much cleaner imagery, which we launched in 2008. And with luck, we will launch, that's not luck, in 2013 we will launch GUI-2, which will have even better native resolution on the imagery. Okay? People ask, I should say, we also have some airborne aerial capability through a company called MJ Hardin that we bought. Satellites are all about 400 miles high. They're going fast. We have a lot of imagery in our archive. We can collect about 7.5 million square kilometers a month. So I got on the web and looked at how much land there was, because imaging the ocean doesn't sell very well. And there are about 150 million square kilometers of land, apparently. So 7.5 million a month sounds like a lot, but you know, it takes you 2 years to get the Earth even at that rate. Right? All right. So we get lots of fun images, right? This is, what is this? This is Qatar. No, Qatar, I think it's pronounced actually now. And it is amazing what they're building in the Mideast, right? There's all kinds of funky buildings that are fun to look at like this. And so that's kind of interesting. I actually look at this image and think, oh, that's going to be a nightmare to extract features from, because it's very, very cluttered and very hard to figure out what's going on. We also do things that aren't quite as fun. After the tsunami in Japan, we were imaging Japan basically all that we could. And if you look at a before and after pair, you'll see this is what this particular scene looked like in 2009. And then after the tsunami, it was just gone, right? And it's tragic. And it also is a very important and tough problem to figure out what's gone and what's still there as quickly as possible. Okay? So, I'll talk a little bit about what I sit around and think about with my team most of the day. We think about feature detection, which I talked about, and the 2 ways to do feature detection. Feature detection. So how's feature detection done now? You look at your various TomToms and various systems. You can see all the roads already there. Where did they come from? The answer is they were extracted by hand, probably in India. And that is expensive even in India to do that, because it's incredibly labor intensive, right? So the question is not can you extract the features, because you know perfectly well that humans can do it, but can you get a computer to do it in either an automated or semi-automated way that's fast enough to compete with human extraction, okay? We worry about change detection, like the image I just saw. If you have a pair or more of images, can you tell me what has changed between the images? And more importantly, what has changed that is significant between the images, right? If the leaves fell off the trees, nobody cares. You knew you imaged the second one in November, right? So you need to try and focus on what you think is significant change detection. There's classification, which is saying I have an image, I want to know, what the land cover usage is for the different stuff. People care about that. So those are sort of the computer vision type problems we worry about. We also have problems like image registration. So this image came off the satellite. Where is it, right? You have two images. How do they relate to each other? Can you merge them together in a correct way? Things like that. There's pan sharpening, if you know what that is. So the satellites I showed you, they image in panchromatic, a black and white image. The GUI-1 does that at half meter resolution. And then you get MSI, multispectral images, which is blue, green, red, and near infrared bands. And that comes in at 2 meters per pixel, right? So it's a quarter of the resolution. So the question is, can you take the high resolution panchromatic image and the lower resolution MSI images and combine them in a way that gives you a nice image? And the answer is the answer is yes. The first thing everyone tries is bilinear interpolation, and it's not good enough, right? So you have to think of something else to do. Okay? The final thing, mosaicing, which I swear is spelled correctly. So the satellite images in stripes that are about 17 kilometers wide and, say 50 miles long, some number of miles long, right? So what you get out of it, and you're flying over these different passes, so you get stripes that you have to put together to make an image of, say, Puerto Rico, which is sitting up in my boss's office. And so you have to take images that were taken at different times, possibly greatly different times, possibly different resolutions, and certainly with a satellite in a different position, right? And merge them together in a way that you get an image that looks correct to the human eye. And there's actually quite a lot of stuff going on there in terms of co-registering the images and things like that. You have to totally balance the image, which is to say you want it to look like it was one image going across, not one part being bright, one part being dark in relation to each other. And then the cut line. So at some point, you're going to have to transition from one image to another image. What's the best place to cut the images so that that looks good? And what you don't want to do is cut through edges if you can possibly help it, because the human eye jumps at that and sees a problem right away. So there are issues about that. Arguably, mosaicing takes into effect the 2 bullets above it as well. But it's a big problem, and it's interesting, and it's a lot of data, so there's sort of management issues as well and high performance issues, and it's fun to think about because we're doing that now. So before I was doing this talk, a couple months before, so I didn't know I was giving it, we were having a debate one day about what math we use the most in the office, right? And we were having a debate until someone said, oh, statistics. And we're like, oh, right. Other than statistics, what do we use most, right? Statistics comes up all the time, all sorts of statistical analysis of the images, analysis of eigenvalues associated with different things of the image, things like that. We deal with road networks and stuff. We deal with things like, well, we do the 6-coloring problem because the 4-coloring problem algorithm is not necessary. Things like that. Componentization, so that's both breaking up stuff where you know how to what the sizes are, you just don't know where the boundary is, as well as sort of segmentation problems. We have problems with smoothing and sharpening images and vectors. We have a ton of minimization problems, right? So what's the cheapest way to get from here to here? What's the closest match you can make between these two images, right? What is the correct weighting for this particular algorithm? And then occasionally we'll be in different spaces looking at things. Fourier space comes up a lot because it's easier to work in there than in the space that the images come in. All right. Finally, we worry about high performance computing a good bit, particularly recently GPU cards. So what you get off the satellite for a single image is usually about 50 gigs of data, right? It's called a Fred file in our parlance. And you have to process that and turn it into an image, and that image will be around 3 gigs probably. depends, but say 3 to 4 gigs for that, okay? So there's a whole lot that goes on in terms of taking this thing and changing what comes off the satellite into something that the human eye sees as an image, okay? And that's expensive, and it needs to be done fast because people don't want an image of what, you know, Denver looked like in 2005. They want an image of what Denver looked like yesterday, right? So the faster turnaround time you can get from satellite to customer, the more valuable your imagery is, okay? So that's a big issue. And there are issues with porting, getting stuff off the satellite and porting it places it has to go and stuff. We also worry about distributed processing. We're using Condor now. We're looking into something called PBS, if you're familiar with this sort of thing, which is a batch scheduling system. And of course, we do native CPU multi-threading. Now, I, by training, am a mathematician, so I felt compelled to put this up. I learned about L infinity and L2 and all that good stuff, right? And what matters at the end of the day is you go down to production, go to the quality guys and say, is this good enough? They'll say yes or no. And the metric they use is, does it look right to me, right? So it's very hard to quantify, you know, if this image looks correct enough. I mean, you can try some techniques that throw up a few artifacts, right? And you may think, I can live with the artifacts because I made this method and I'm in love with it, right? QA/QC will take a look at it and go, no, we're not sending that out the door. You got to do something else. So that sort of stuff, I mean, you can measure sharpness of images. You can do some things analytically with change. But in terms of what a human sees as a good image is still a very nebulous, poorly defined norm. Okay? All right. So what I'm going to do is just sort of outline a few of the problems with nice, colorful pictures that we look at. And then I'll spend sort of the second half of the talk going into detail about one particular method, which I hope isn't too mathematical. I kind of doubt it. So classification. The problem is you have this image, right? You want to know how the land is being used. Governments care about this a lot. Not only the federal government, state and local governments care a lot. We image at a ½ meter per pixel. There is something called the, let's see, National Land Classification Database, NLCD, I think it's database, which is a, for the US, at 30-meter resolution, they classify every point, every pixel in the US, how it's being used, right? 30 meters is fairly coarse, right? And it's not, well, how accurate, how good a job do they do is unknown. Certainly, when we look at different pieces of it, we go, oh, well, that's completely wrong. But we were looking at 2001. They did another one in 2006. You don't know that the land has changed that much, but you suspect some of it hasn't changed that much, right? And then how do you verify the results? So here's what you don't want to do to someone who works for you. Hey, Phil, sit down there and classify each pixel in that 3 gig image for me, right? If he doesn't kill you, he'll quit, all right? So it is almost impossible to generate a truth data set of any significant size with the resources at our disposal, at least. So what you can do is you can take a subset and look at just that and say, how did we do on this smaller thing, and hope that extrapolates to the image, which may or may not be correct. But to actually sell it to a customer, you'd probably have to do a better job than that. So the secondary problem with, okay, can you give us confidence and speed up confidence intervals for each classification and get a more efficient QA/QC procedure so we could sell it? And you ask, could you really sell it? The answer is yes. Well, let me talk about this in a second. So this is the truth data. This is something that the government produced in 2001 at 30-meter resolution. Okay? That's Boston Harbor, if anyone cares, if you see the T. The MSI image, this is what would come off a satellite. Okay? It's in RGBN, so it's 4 bands, so you're looking at the near infrared, which is why it looks a little funny, and some other stuff, right? And this is Icono, so this is at 1 meter resolution. This is a DEM, a digital elevation model. Questions? If anyone has a question, feel free to yell them out. Some of you are familiar with my policies on that. Digital elevation model is a map of how high the world is at every point at some resolution. Okay? And we use that when we try and construct this thing. Okay? This is what we do. Do a segmentation algorithm to break it up into little pieces. This piece is really big. You can generate a water mask fairly easily if you have near-infrared data, because the near-infrared band returns a low signal off of water usually. And then you can derive things like vegetation features, urban features, and a land classification. But we don't live in Boston. We live in Colorado. So here's Fort Collins. And you ask, why Fort Collins? And the reason is there's utility companies in Fort Collins that want to know how permeable stuff is, right? Because they can bill based on water runoff. So there's a commercial market if you can do this well enough. Now, I'll tell you a story about that in a minute. But we started with Fort Collins, okay? And this is our first indication, doing the procedure you've seen before, of the permeability. So the darker red areas are non-permeable, okay? So things like roads and high density developed areas will come back red. Things that are open space will come back in this light gray color like that. And you can make out basic features. And we were very happy with this. And we showed it to the customer. And they said, no, it's not good enough. Resolution is nowhere near like what we can bill for. So we said, OK, thank you. We also did the classification as well. So you can see. And here is the different. It's not very important, but the different colors mean different types of development. So note that the red ones there are development intensities, basically. So we went back to the drawing board. Not back to the drawing board, but somewhat back to the drawing board. And there's a place called Big Spring, Texas. And why do we care about Big Spring, Texas? We care about Big Spring, Texas, because we have a verification point on that runway. Okay? And so every so often you fly the satellite over and check its accuracy, which means we image Big Spring, Texas all the time. And we have a whole lot of data on it. And we can have it during all the seasons and everything like that. So we said, all right, let's go back to this and see if we can do a better job. And we have a better job. We have a higher resolution. We haven't shown this to the customer yet. We have higher resolution data. You'll notice if you look carefully, you can see the stripes on the runway. That's bad, right? Because those stripes are not, ground. Those stripes are still runway. They're painted wrong. So we don't have it perfectly yet, okay? But we're doing a better job. What they would like to do is there's a permeability map. They'd like to take, everyone's, parcel of land, superimpose that vector file on our permeability, add up, how much permeable versus impermeable stuff they have, and send you a bill, right? Not you, but companies. So things like this matter. At least they matter to some people. Okay. Speaking of airport markings, this is a line of business that companies in for a long time. People care about airports a lot, right? People build models of airports a lot. Vector data about where features are, including runway center lines and sidelines and everything, go on board the airplanes. Airlines buy this data from you, okay? So there's a big market. They're about, I think they're about 1 to 3, number said 1 to 3. I think there are about 1,000 airports that are really high volume busy that people care about a lot. 1 to 3, they're sort of 9,000 smaller ones and 14,000 after that. If you look at airports in this country, they have nice markings on their runways. If you look at airports in other countries, they're not necessarily as picky, right? So algorithms that we developed to work in the US work pretty well in the US and pretty well in Western Europe and places. And I think we looked at a runway in China and discovered, hey, no edge markings. Hey, no centerline markings. In fact, they're just some piano keys, and it looks like there are people walking across it, right? So the other thing you discover, I guess I should show you, let me push down a little bit here. So you got to nail the accuracy. If you want to do this automated fashion, and we're doing it, but you really, really have to get the accuracy correct, okay? Because planes are using this to figure out how to land, right? That said, even if you could generate it all automatically or semi-automatically, it still wouldn't go out the door without somebody looking at it, right? Because the legal liabilities are simply too big, right? But it would be nice if you could have sort of a starting point to look at, maybe compare it to previous existing data, mark what's changed, what's different, have someone review it and say, okay, you could speed it up, make it much more cost effective. You could also think about doing this fully automated, which we looked at. You can do it. The problem with that turned out to be that a human looks at an image and says, oh, there's a runway. I can click on the 2 piano keys and you do your stuff. Piano keys are the stripes at the end of the runway. You give a computer an image and it starts scanning through the image line by line to try and find a runway, which A, it may not find, and B, takes a long time, right? So there are issues with trying to get a more efficient search for runways. And there are questions like, well, could you use a digital elevation model because runways tend to be flat? But it's probably more cost effective to let a human start the process, right? At least that's what our conclusion was. But it's fun to think about how to do that. I think this is Perth, Australia. Okay? So what you're seeing is if someone were to click on the piano keys here and here, and then here and here, and let it extract automatically, you would see those vectors. And if you zoom in on those vectors, so this is internal code that we have, we're getting extractions that look like this. Not too bad, but not great. Perth was the first airport we saw that decided to flare out their sidelines on us at the end. We caught it, but we didn't catch them correctly flaring back in, right? So it's not good enough yet. We're doing pretty well in the center lines, and they want all of this, right? We don't have the numbers yet. We think we know how to do that. You can do object recognition on numbers. That's fairly well known. But we haven't had the time and the energy and the budget to put into that yet. So it's interesting to me. Harder problem is change detection, right? So you have a couple of images. You want to know what's changed, right? So there are all sorts of preliminary issues with this, right? Were the images taken at the same time of day? No. Was the weather the same? No. Are there clouds in one and not in the other? Yes, right? There's all that stuff. Cloud detection, I didn't talk about that. Cloud detection is a big problem. Human can tell you where a cloud is easily, but it's hard for a computer to do that if there's snow in the image, right? And some other things. You get gray clouds too. All right. So what we do is we try and break things into objects, right? We try and have some sort of, because you compare pixel by pixel and you say, oh, this pixel value is different than this pixel value. It doesn't do you any good. But if you compare by, on an object level, we think you have a better chance of doing what you need to do, right? And that's what that third bullet's about. Well, how do you do that? So what you need to do is you need to get a segmentation. Does everyone know what a segmentation is? Yes, I know what a segmentation is. You need to break the image up into little pieces and then possibly big pieces as you stick them back together. Well, how do you do that? There are lots of different ways to do segmentation of images. We're doing some graph-based, but we're doing algebraic multigrid. Because we have multigrid people trained here who are very big on multigrid. And it works pretty well. Okay, you can break up images using multigrid, associate the smaller images together to build a coarser level and say, okay, we have something reasonable here, right? We are also trying to combine that with some linear extraction stuff that I'll show you in a second, right? And with the land classification. Because you can do a better job of change detection if you did a better job of land classification to begin with. Because if something was classified as, I don't know, a forest, and it's coming back as high density urban, you're pretty sure something changed in between those two images. So we're trying to combine it with that stuff too. Okay? So we also have a component where it tries to learn from its mistakes, which is common this thing. I can't say we're proud of that because we like to get it all at once, but it's a practical approach to say, all right, we've got something workable. This slide, if anyone remembers Patrick Young, it's courtesy of him, gives you an idea of what we do. So you have these two images. You go ahead and co-segment them. So you have a way of segmenting sort of both together, and you mark the segments that have changed. Okay? Not too hard, you think? Well, so here's an image of Karachi that we actually tried to run it on, did decently. You look at that, and I didn't have the second image, but the second image looks pretty similar to this from this resolution. There's the size of stuff of the image. I should say, 13,000 by 13,000 is not a big image at all, right? And this is only a very tiny piece of the city. So you have to imagine applying this thing to very, very large amounts of data. Well, if you do that, we have some places circled where we've detected change. That's great. And if you look carefully, hopefully you can see on the screen, it's a little bit tough, there is some pink in those areas that we have circled. And if you look more closely, you'll see that there is pink in areas that we haven't circled, which is unfortunate. So that's what the algorithm came back with and said, OK, this is change. Well, it turns out that the other change was shadow effects. Shadows are an enormous problem for this sort of thing, right? They cause all sorts of issues. They're very hard to remove fully, and they show up as artifacts in what you were doing. So we're actively trying to figure out what to do better with that. Okay. The road tracker, near and dear to my heart. Time-wise, that's just sort of an overview of the slide. But here, assuming this thing will play, come here, mouse, is what the road tracker does. So what this is both a semi-automated and automated feature detection. It's a commercial tool now. We sell it. You can buy it. And I'll talk more about it in a minute, but you can see it extracting roads. And it's extracting roads with a click mostly on one end of the road and then on the other end of the road. And it's figuring out the path it needs to take between the two. Okay? I hope you're impressed, because this was very hard. This actually here, this part is a pure spline. This is not using image information. But what you saw before was using image information and we'll see it again in a second, to extract it. So where is this? This is the Khartoum, another place I'm glad I don't live. And if you notice, it's sort of a very cluttered urban area, right? And if you wanted to extract a road network out of here by hand, which I personally have done more times than I care to count now, well, because we do timing runs, it's a little bit mind-numbing, and it's hard to keep focused, and it takes quite a while. But with this sort of thing, you can get it faster. We also have a cleanup tool built in here. This is, again, there are issues when you have a network and you're merging them together of how to do that effectively for roads and how to clean up the topology of intersection and things like that. So that's done, and it's done at such a level that hopefully you don't even notice it here, right? But we have things that do that. Let me get to 2 more bits here. We'll have to run at the end, but that's OK. So anyhow, you can clean up your vectors as well. So I should say you have an underlying image, you have a vector like this. This is a fully automated extraction. This is part of Las Vegas. You can simply highlight the area you want. You click Go, which you can't see, and there's edit out 30 seconds of pause time, and then you get that road network. That was very hard, and we're very proud of it. This last piece is if you had vectors already there that were off. If you look, it might be hard. There are vectors there, but they are not on the roads. They are misregistered, and they are also overly generalized. So we have what we call a vector update tool, where you can take that, you click on our Go button, and it fully automatically generates or corrects your vectors. If you look carefully, it missed one vector because it was a double lane road that it couldn't handle, but it got the rest of the vectors updated pretty well. That movie is courtesy of Josh Nolting, if anyone here remembers him. So, going boldly on. So we've seen it speed up about a factor of 2. It's difficult to get production people to do the tests more than about once a year because they don't like extracting things twice. But we can do things like that now. All right. So let me talk a little bit about this now. So you just saw that, and that's all well and good, and it looks hopefully impressive and probably easy. What's really going on? So what you're going to get from a standpoint of a programmer is you're going to get a series of mouse clicks, right, on an image somewhere. And then you get a double click at the end. It says, OK, figure out what the best way, the best path is. What does that mean, right? Well, it means a couple of things. Well, one thing. So what we've done, and I haven't showed you this, is we've generated for each image support files that give us ideas of where we think things like roads and buildings and other important features are. Okay? So we have that. We have, if we wanted, possibly spectral information about the imagery as well, right? We have all that information, and we use that to build essentially a cost function, right? Saying, okay, we'll go from here to here. You have those series of clicks. You say, okay, I have a cost function. I have a series of clicks. I need to find the best route, which is a minimization problem, basically, right? So you haul out what? You haul out Dijkstra, right? Or something very close to Dijkstra. You say, all right, let it run, see what it can get back. So we're doing a whole lot of work, right, on this simple mouse clicks to get that there. The underlying mathematics of doing that extraction is, in my opinion, fairly interesting and challenging to get done correctly and speedily and things like that. And then you can play around with, well, do we want Dijkstra, do we want A star, do we want, if you know what that is. There are different ways to attack that problem, right? But they all boil down to how can we find the least cost path. We can skip that. That's just, we've seen stuff like that before. That's a vector update slide. All right. So this, let's go ahead. Let's skip ahead a little bit. Well, let me pause for just a second. My background is in partial differential equations, so I am biased in that direction. So of the techniques we use, I wanted to talk mostly about, the one I wanted to talk about most was this one, right? So the question of how do you build those cost functions? How do you find out where you think a good piece of, say, road is, right? How do you do that? Well, there are a lot of ways, and we use a lot of ways, but one way you can do it is you can say to yourself, thank you. I'm going to, are we playing? Let's go ahead and play now. Okay. So I'm going to start at a point. I'm going to let myself flow along. I'm going to flow along until I hit some sort of stopping criteria. And what you can see are the red points are the points that have been identified as, well, technically as low cost compared to where you started. So for our purposes here, road. The blue boundary is the candidate points that might come next, and yellow is just I've stopped it, and that's what you get as something that you might mark as low cost to begin with. Show one other piece of the video and stop this one. So just generating a cost function, just getting an idea of where these features are is a non-trivial problem. So where is this? I think this might be Littleton. I'm not quite sure. I don't remember where the first one was. So anyhow, it's the same sort of idea. You can see yourself flowing along. You'll notice as it gets larger, it gets more, it gets slower. Does anyone have any ideas why that might be? No talking. Seriously, anyone feeling brave? No? At the end of the day, you're doing a boundary search, right? And as this grows, the boundary is growing rapidly compared to the area because you're usually looking for thin features. So it gets cost prohibitive to do this for extremely large networks if it could flow everywhere. So then, okay, can we do it on subnetworks? And then how do we get seed points? Those are all sorts of problems we worry about, okay? So there's a lot of stuff like that. All right, now you're going to stop liking me, because I know you all like me now. I'm going to talk about the level set method. This was Sethian and Osher, probably the two biggest names. But there's a large set of literature dealing with how level sets work, and it's been used to solve all kinds of different problems with relatively high success, right? So the basic idea is we're going to imagine that we had some sort of function, which is what this red thing is going to be, and we're going to see how a level set in that function evolves. Okay? And it can evolve in a variety of different ways depending on how we state the problem, right? But rather than solve for the evolution of solution of a problem, we're going to solve for the evolution of a level set, is the basic idea. Right. So let's start by thinking about this. Imagine you had some sort of level set there, right? And it was flowing outward with speed f at every point. F can vary, but it's going outward at every point, right? Can we figure out where that curve is later on? Well, you can. I should mention that the curve, something very nice about level set methods is, well, the curves have to be closed. They can break into pieces and form back together, right? That's actually quite a cool thing that it can do. Okay. All right. So if you think about this, we're going to start by assuming that f is greater than 0, so we're flowing outward, right? We know, at least in one dimension, that velocity is dx dt, and we said that was f, so we have the following not overly tough equation. We can invert it and see that, aha, dt dx times f is equal to 1. And yeah, you have to worry about the inverse function theory, but remember, you're always positive, so you're flowing outwards, so you should be okay, and you can in fact prove that. Okay. That's wonderful. Now it's interesting to me because a mathematician, I spent a lot of time thinking about 3 dimensions, and I'm back in 2 now with these images, right? But that's okay. This applies to higher dimensions as well. So if you take the analog, if you think about t as being the time at which your level set, your boundary, would cross the point xy, okay? You can imagine solving for that, and you find a completely analogous situation to what I put up in 1 dimension, right? This is called the boundary value formulation of the problem. And solving it, exactly this, is how I got those movies I just showed you, okay? Solving this is what solved for the evolution of that front on that image. Okay? Now, I feel compelled to show you this, although I have more slides I don't expect you to see later if you care. What if f is not strictly positive, right? Well, you can't use that statement of the problem, but you can think more generally about, all right, imagine some function phi, and we know we have a level set of phi, so we can go ahead and take a derivative of that equation on phi and discover the following, not overly spectacular thing by use of the chain rule. Well, I look at this and I start to drool, right? Because this is what I spent many years of my life doing. I think, aha, advection equation. Only, of course, it's a little bit harder than straight advection, but nonetheless, it's the kind of thing that lots of people have thought about before. So you go, all right, something is moving along with a given speed. We know that our flow is in the normal direction, right? And if we plug that in, do a little simplification, we find, aha, we have the following equations to solve. Okay? This is called the initial value problem, formulation of the formulation, right? And if people in the audience care, it can be related to the Hamilton-Jacobi equations, right? So there you go. Question you should always ask me is, so what? Because I like to talk, right? So what? Well, this is an idea. This idea was put forth, I think, first in the 80s. I don't think it predates that. But you can use it for 2 things. You can use it for cleaning up a noisy image, right? And I have slides that I don't intend to show, but the smartest idea, well, one of the smartest ideas, and that is, how would you flow to clean up noise in an image? And what they said is, what if you flow based on the curvature? Well, wait a minute, I know if you flow based on the curvature, you contract to a point. That's not very interesting, right? Well, okay, but what if we flow with some sort of max-min function on the curvature? Could we get things to regularize and things that were just noise to go away? And the answer is yes, to a large extent, right? And there are other issues with that. So that's been used to clean up noisy image. There's segmentation, which is what I just showed you the movie of, right? Can you use this to flow through an image and pick out sort of similar typed objects to segment? And that's what we're using it for, okay? You do have to pick F, because without F, you don't have any way to flow. Let me do a little more detail here. So you have this equation you want to solve. You can square it to solve this, and you have your gradient operator. There are multiple different ways. So let me say this. We're working with pixels, right? We have a grid laid down, and on that grid, associated with either the center or the corner, depending on your personal preference, is a value, right? That is inherently a discrete problem, right? There is no notion of a continuum of pixel values. It's 37, and then it's 92, right? You got to live with that. So how do you approximate the gradient? Well, if you know numerics, you know there are a bunch of ways to approximate the gradient. For the method I'm talking about, you're imagining sort of a front flowing. It turns out you hit the same sort of upwinding issues you do with other types of hyperbolic PD stuff. So you do have to think somewhat carefully about what you mean by that gradient. Okay? So there are issues like that I'm not going to dwell on, but there's stuff there that you need to think about. Okay? Once you do that, you can say to yourself, all right, I have that. I know that my front is here now, so I want to go ahead and let it flow out. So I've sort of marked, the green ones are places you've been, the red ones are the possible candidate. This would correspond to the blue ones, since I wasn't consistent, that you saw in the video. Right? So if you have that, you can go ahead and you search over all the bands, all the possible boundary candidates, right? You find the smallest value of t time for all those cells, pixels, right? You then add on there and say, okay, now I just have to recompute the time value for all my neighbors. This is very similar, although not identical, to what the Dijkstra algorithm does, right? It is another variant of searching sort of a neighboring things to see what's cheapest and adding it on and then continuing from there, okay? So there are many analogies between Dijkstra algorithm and what we're doing here. As a mathematical detail, you do need to check that your time is always increasing as you go through here. It boils down to solving various quadratics for various different possibilities of your 4 boundary cells. And I should say you only flow to those 4 boundary cells. You're not flowing diagonally. But there you go. You can have that. Okay? Finally, as I believe I said, you need to pick a speed that you're going to flow with. Okay? Yes, lots of math here, and I haven't defined all of it, but I'll attempt to do that now. Sethian suggested this, right? This is some sort of Gaussian with some spread sigma convolved with the image. You then take the gradient of it. What does all that mean? If you think about it for a little bit, it means that where you have a sharp boundary, you will have a very high cost. And it will take a long time to flow across that boundary. Okay? He also adds in an attractive component here. He was probably thinking about medical imaging when he first did this, where you want to get sort of to the boundary of your spleen. We don't image any spleens, but you can. And then this is a parameter. Here's the curvature raising its head again. This is another parameter determining the attractiveness. So that is not what we choose when we flow. What we actually choose is undoubtedly proprietary, but the idea is, okay, can we find areas that should be high cost? Does that correspond to ridges? Does that correspond to rough texture? What does that correspond to? And another sort of more annoying problem is, what if you had, a road flowing along fine, and then, hey, there's this little driveway that goes to a path that goes to another road, so it flows somewhere it shouldn't, right? So there's also some work that we do to try and close off very small openings for this flow, because we're interested in coarser features like that. Okay? So we have all that. All right? One final logistical detail before I lose all of you, or maybe none of you, is a heap sort. right? So this comes up in Dijkstra, it comes up in this method as well, the flow. You need to have an efficient way to keep track of what the cheapest value is, right? And when you add a boundary pixel to your flow and then take its neighbors as your new boundaries, you know that all of those, because you've proved it earlier, that all of those times are necessarily higher than the time that you just added, but they could still be lower than every other time, or at least some of the other times, for all the other boundaries. So you have to go do a heap sort to figure out, okay, and once I add these on, what is the cheapest time to get back to where I started? Okay? So there are all sorts of things like that going on. So, what kind of questions are there? They're big overarching questions, but there are also some small stuff that we thought about more or less recently that we thought, hey, we'll throw out here. Maybe one of you guys will solve it and give me a call. Can you make the level set method faster? So I said as it got larger, it got slower, and it gets slower quickly. Okay? So in terms of using this as a general solver for cheap area, it's bad because it's too slow. It works great, and it doesn't run fast enough, right? So you might say, well, could you make it faster? We're pretty sure the answer is yes, right? You can think about saying, all right, well, say I have a GPU available, right? Can I use that to speed things up? We think we know how to, we haven't tried it. We think we see one way to do it, okay? Dijkstra and similar things come up all the time. Can that be parallelized? Well, don't know. Don't think so, actually, but maybe. Someone could tell us, we'd be very happy. Something that came up last week. You guys know what a JPEG is? Yes, yes, you're all young. My mom doesn't know what a JPEG is, but she's 82. So images are getting bigger, that's a problem. So compression is becoming more and more of an issue, right? So if you want to compress this thing, well, JPEG 2000, I think it's based on, has a new wavelet compression built into it, right? But it's slow for us, because we're looking at, I mean, say you got a 10 gig image, right? You want to compress it, it takes a while. Well, can you use a GPU to make that faster? Probably. We have not fully investigated yet, but it's the kind of thing that comes up. It's like, oh, sort of an interesting question and would be really useful for us tomorrow, right? But those are the sorts of things. So, okay, conclusion. Everyone smiling? Good. So that's what we do, right? Those are the kind of problems that I work on and our group works on all the time. Find it enjoyable. There are lots of them. There are more. I mentioned cloud detection, which I actually didn't think of when I was writing this. And the other thing, so let's see. We have a couple of PD guys. We got physicists. We got some computer science people. We got graph theory people. All kinds of different methods have proved useful for us from all kinds of different fields. No, not symbolic logic. But everything else we've sort of thought about and said, yeah, that actually is useful to attack this particular problem. So one of the neat things about this, as this seminar has probably showed you, is that many, many, many different ideas can be applied, and you don't know when they're going to show up, because the challenges and the types of things we're asked to do are always changing and always interesting, I think. So I've probably said too much. So are there any questions? Well, go ahead and applaud. Yes, okay, good. Are there questions, comments? I do weddings, bar mitzvahs. Yes, brave lad.
You mentioned classification, but you didn't really describe the kind of techniques you're using. Are you using syntactic or statistical? Are you using nearest neighbors? Are you using support vector machines?
We have not played with support vector machines yet at all, though we downloaded software to do it and never got around to it, right? So we're doing a combination of sort of segmentation with statistical basis, I guess you'd say, right? So you say, all right, you need to, we are trying to build sort of a tree that shows you all the different pieces, and then maybe you have to aggregate them more and get statistics on them, and then try and figure out, was that a good place to stop? Should you add this other hunk into it? Things like that. I'm not, so let me tell you, the more recent images, the finer ones, I haven't worked on, okay? The older ones did a whole lot of statistical analysis and less segmentation. And my belief is that we've gone to more segmentation before we do statistical analysis, but I'm not 100% sure of that. Does that help or?
Can you say anything about the representation, or do you just go into abstract high-dimensional spaces and do statistics in nearest neighbor, or do you have other kinds of representation or classification?
I think I can say stuff. So we have a tree that has all these leaves coming off of it, or a tree goes down to leaf level, right? And then we say, okay, we're going to prune up from there to what we think is something that represents an object, right? And whether or not, when we think we have something that's sort of at an object level, that is done on a statistical basis, right? What's the variation like within this? Does that make sense? Yeah. So we get to that level, and then we say, all right, what other information do we have? So we have a water mass. Do we intersect the water mass, right? We have information about the homogeneity of the color, for example, within that image. Okay? You still don't look happy, so maybe I'm not saying enough, right? No? Yes? Maybe?
So are you basing this on the local topology of a few pixels, or how big of a classification problem are you?
We've played around, so the answer is no, not a few pixels. That doesn't work. At least in our experience, that doesn't work, right? How big, well, the number we're actually using is probably proprietary, but you want to have enough pixels that you have what you believe is a statistically representative sampling of that area, right? And that number, of course, changes depending on your resolution, right? So if you would want 4 times as many for the half-meter imagery as you would for the 1-meter imagery, right? So let's see. If you go back, where was that image? If you go back, where is the page up? There we go. If you go back and look at the one with the airport, you'll notice that those airport lines came out as different. Let's see, that was up at the beginning, wasn't it? Came out as different, there we go, as different segments within the image, right? Now, I don't know, this is 1-meter resolution, so I guess those are, I don't know, 3 or 4, probably not even 3, probably like 2 pixels by the length of the runway. So they're relatively small segments. Let's go up to the next one. They're relatively small segments. But the runway, or this is actually the terminal building, came out as one huge segment, right? So there is a criteria where we say you have too few pixels, we're not even going to think about you, right? You have to hit a minimum size. Once you do that, we say, all right, do we think you should be aggregated with things that are nearby based on a variety of criterion, or are you different enough from your surroundings that we consider you statistically unique and we're going to keep you as a segment? Is that better? Okay. Anything else? Yes?
So if you have, let's say, medical imaging in Oregon,
Mm-hmm.
it's easy to see how the level set work.
Mm-hmm. We are jealous of medical images, yes.
But here, you've got a whole block sheet sets, so do you use level sets on a very localized region?
Yes, for 2 reasons. One is the reason you said, right, that we don't have sort of an organ. I mean, you look at a liver and then it's dark and it's next to a spleen that is brighter or something like that. Medical imaging is hard. I know I want to disparage medical imaging. Okay, it's also much more profitable, right? But to us, it appears, and they're usually doing it in 3 dimensions now too, which we're not dealing with, right? To us, it appears much less cluttered than what we have to deal with, right? And we don't, our test problems are people from sales or production going, hey, what can you do with this, right? So we don't get to pick them ourselves. I mean, I guess we can pick the type, but not always the images. So yes, and so what you can do is you can let it flow a little bit. And so I didn't talk about this. You need a stopping criteria for these flow methods, right? And you can stop when you want to stop if the time gets too expensive, because that means everything around you is very high and you shouldn't get over it, right? Or you want to stop when you have too many pixels, is what we usually use to cut it down, right? We say, all right, we're going to flow this much and say, that's enough, forget it, right? We don't care if you can find more. The downside of that is you will have to get another starting point to do it, and then you're repleting your flow again and again. But that also helps overcome the problem with the expense increasing greatly with the boundary search going up, right? So I know Sethian has a book where at least one chapter talks about how to use these things in medical imagery specifically, right? I don't recall if I've seen something where people talk explicitly about using this in satellite imagery, but we do, okay? So how's that? It's not new to the image processing community in any way. Everyone's so quiet.
We have time for one more question.
The host is desperately pleading for one more question. Let me ask you guys this. What sort of problems interest you? You came to this seminar, right? What do you care about in imaging? Anyone? Anyone? Bueller?
Getting rid of noise.
Ah, getting rid of noise. It's like I paid you to come here. These are the slides I wasn't going to show because I thought it would go too long. Plus, you're all asleep after the other stuff. But you can, so the initial, so let me tell you this. Radar imagery, which we do work with, is very spectral, but there are known ways to help deal with that. If you'd think I'd go to the different thing. Hey, everybody get that? Great. Where are they? Yeah. Oh, here we go. Oops. So, if you imagine, so you can imagine evolving, imagine evolving under curvature, right, in these things. And you can do a test on things like, so say you had this image, and you stuck in a whole lot of Gaussian noise, right, which I did. And then you do what it says to do for the curvature flow. You get that back out. It's not perfect, right? But you can say, all right, I can see with my eye what that original image was. Now, being able to see with your eye and being able to have the computer detect what it is are, as far as I can tell, two disjoint things, right? But nonetheless, you can see there is some efficiency, not that one, efficacy of this sort of thing. There are parameters to tweak with. How big a stenciler to use? Do you bias the curvature one way or the other? The things to do. Is this the best way to do noise reduction? I don't know. Okay, this is simply the one that I played with. But it is used, and there are papers claiming great results. Whether or not you believe that, well, go play with what you got now. This is a level set method for noise removal, or image enhancement, it might say. Not this example, but the paper, if you go to, what's Sethian's first name? Sethian, he's at Berkeley. Go to his homepage. He's got a lot of his papers up on his page, and you can just grab them easily. It's nice that way. And it's not terribly difficult to go through either, right? You don't need the whole full PD background. I don't know what it is, but it's fairly well written up about how it goes. And it's not, it always, even the images they show, there always are some speckles around still. But this was, a fairly noisy image to begin with, right? Looks better without. Right? Right.
Thank you.